basic public key crypto. So what's missing from this scheme?
Key distribution.
Key distribution, right? I mean, public keys. All right, I somehow had to have the Purdue EDU key to authenticate the record. Okay, maybe I'm configured with that. But how many DNS zones do I visit? You know, of the billion records, we're divided into several tens of millions of zones. And chances are I don't have the public key for every one of those tens of millions of zones. So I need a good public key distribution system. Here we have a nice advantage. We already have a natural hierarchy. If we assume that everybody knew the root key, which is not such a bad assumption, because right now everybody who's a cache has to know the IP addresses of the root servers. That has to be hard-coded. So now we're going to hard-code in a root key. If we knew the root key, and we have a rule that every parent signs their children, we can actually build the system, and starting from the root, we can walk down the tree and find any DNS record we want. So if I want to authenticate www.purdue.edu, I'm going to start from my well-known root key, and I'm going to ask for, what's the public key for edu? What I'm going to get back is the edu key plus a signature from root. So now I can authenticate edu. With the authenticated edu key, I can go off and I can ask for the Purdue edu key. Purdue edu is signed by its parent, edu. So now I can authenticate Purdue edu key. And finally, the record I want, www.purdue.edu IP address, or its A record, is signed by the Purdue edu key. So I have a nice authentication chain starting at the root, walking down to edu, walking down to Purdue, finally walking down to the data I want. Make sense? Okay, so this is all something that you would expect almost an undergrad crypto class to come up with, right? I mean, this is not rocket science at this point. This is basic cryptography. The way we actually put it into the zone is, not much. I mean, this is just to give you a sense that this is really a standard. These are real records. So here what I have are the A records. And below the A record is what's called the RRSIG record. So the new resource record signature. And this signature has an inception date of October 27th, 2004, an expiration date of November 26th on 2005. So that's when this record is valid for. I know who signed it. It's signed by a key named Purdue edu with tag 468. So if you find that key, you know how to authenticate the data. How do I know that's the right key to apply here? Right, so this signature basically tells you, here's the signature for the record you're asking for. And the guy who signed it is the guy in red, key 468 from Purdue edu. What if I could sign this with any public key, right? I could sign it with foo.com or darpa.mil, name your favorite zone. So how do I know this is the right one? I mean, it follows almost directly from the name, right? I mean, who gets to sign the Purdue edu information? The Purdue edu zone. So I have to be able to assert that www.purdue.edu is actually in the Purdue edu zone. So to do that, basically, I need to go to the edu people. I need to get the existence of a Purdue edu key that's authenticated proves Purdue edu exists. And now I can ask Purdue edu, have you delegated this away? If they've signed it, they haven't delegated it away. If they've delegated it away, instead of getting a signature here, I'll get a referral to another key that's signed by Purdue. So I can distinctly draw a zone boundary and tell who should sign every record. I can also store the public key in the DNS. Since it's public key crypto, I don't care who knows it. I want to make it publicly available. So in addition to sending you back the answer, I'm going to be nice, and I'm also going to send you back the key that you can use to authenticate this and the signature. And, of course, the important part of the signature is that it's signed by edu. So if I knew edu key 569, I can authenticate the Purdue key. If I know the Purdue key, I can authenticate the www record, and I'm done. Recursively, I can authenticate the edu key from the root key and back up all the way to the top. Make sense? Still, nothing new here. So we will add one little trick that's worth actually, some some note, and you probably have to scratch your head a little bit to figure this one out. So what if I ask for a typo? Dub purdue.edu. So I basically, this answer does not exist. And I want an authenticated proof that guy doesn't exist. The challenge is the private key's not available. Right? And that's there for a very, very good reason. The way we've deployed DNS, if you're running DNS correctly, not all of the Purdue EDU servers sit here at Purdue. Because if they do, a single network failure takes them all out. The servers should be spread apart. A few companies, large software vendors, have learned this kind of the hard way by putting all their DNS servers on the same subnet or behind the same switch. But essentially, if you spread out your DNS servers, you've got great robustness against network failures, but spreading out your private key isn't such a good idea. So if I have Purdue servers, 2 sitting here at Purdue and 1 sitting off at Hopkins, I'm maybe okay putting my private key on the master server at Purdue, maybe okay putting the private key in the backup, almost certainly not okay giving the private key to Hopkins. So I can't have the private key at the server. Also, if I do put the private key in the server, in addition to simply the distribution problem, now I'm asking the server to do new computations. I'm opening up potential holes for distributed denial of service or simply added load on the server. So there's no private key. No private key at the server, but I still need to prove to you Purdue doesn't exist. Now, I can't just have a generic record that isn't tied to the name. Whatever you requested without specifying the request doesn't exist. Because if I do that, what's the attacker going to do? Replay that when you ask for a legitimate name, like right? So I've got to somehow tie it to the name, and I don't have the key online. And I don't know you're going to ask for dub. Actually, dub, maybe I know you're going to ask for, right? Maybe that's a common typo. But how many typos could you possibly put in? Well, that's pretty much an unlimited set, and I'd like to give you an affirmative yes/no answer for any query you ask for. So given this, what do? Here's the query. Dub Purdue EDU. Doesn't exist. I need to prove it. I have a public key system, but the private key is not online. You didn't know I was going to ask for this record. Anybody have an idea on how you can actually prove this thing doesn't exist? Okay, so the solution actually is not immediately apparent, but will be entirely trivial once you see it. So here's the idea. I know what's in the zone. Let me, instead of trying to authenticate what doesn't exist, let me order the zone in a nice canonical order, essentially alphabetical order, plus a little bit to handle DNS issues. And now I can tell you something like, for instance, in the zone file, there's some entry at u.purdue edu, and the next entry is at dub. And I know this ahead of time, and I can sign this ahead of time. So if you ask for anything in the range between u and dub, I can just replay this signed message. Make sense? So what happens is along comes the resolver. He says, I'm looking for dub Purdue edu. It goes off, and what I get back is an answer. This doesn't exist. Can't sign that part of the message because it's sort of dynamically generated. Plus, by the way, there is a name called u, and the next name after u is dub. That's pre-signed. That's already loaded in the server without having the private key online. That's returned. If the answer you looked for did exist, this wouldn't be the interval. If dub did exist, it would say u, the next name is dub. Make sense? Yeah.
What if your domain, people change their DNS records, right?
Yes.